Today we are opening up some essential sources on a topic that, well, it might sound a bit dry, but honestly, it's the bedrock of long-term commercial asset value.
That's right.
We're talking about the complex world of commercial building insulation requirements. We want to give you a kind of fast-tracked understanding exactly why something like an R value really determines the lifespan, efficiency, and, comfort of pretty much every major structure.
Absolutely right. Our mission today really is to unpack the guidelines that architects, contractors, owners use. We're focusing not just on what the code says you have to do,
Right.
but also the practical challenges, the real world stuff,
Right.
and the high impact solutions these sources point towards. This knowledge, well, it's what separates a building that just scrapes by code from one that's a genuinely high performing asset.
And why does this matter? Like right now, commercial insulation, it isn't just about maybe managing a summer cooling bill, is it?
Not at all.
It's a high-value system. It manages heat flow, or maybe more accurately, it resists heat flow across the entire building envelope. And that includes, the massive surfaces of walls, roofs, floors.
Huge surfaces.
If you get the system wrong, you're basically hemorrhaging energy, and you risk major durability issues too, like moisture damage.
And that system, it's primarily dictated by the 2018 International Energy Conservation Code, the IECC. The core message there is, well, it's pretty clear. Proper insulation is mandatory.
No getting around it.
Nope. It's the key mechanism for hitting those minimum efficiency requirements, driving down life cycle energy costs, and, importantly, ensuring occupant health. We're kind of moving past just basic standards now into a new era of thermal performance.
Okay.
So let's begin with the foundation, right? Code adherence. Building codes, they establish clear, measurable benchmarks. And the most critical benchmark, that's the R value.
The famous R value.
Yeah, it's just a straightforward measure of thermal resistance, basically. How well a material slows down heat moving through it. Codes are specific. They tell you the minimum R value needed for walls, roofs, floors, and it's customized by climate zone, which we'll definitely get into.
Okay, and the IECC, it isn't just a list of numbers. You said it's more like a strategic shift. When we look at the recent IECC updates, what's the one provision you think that causes the biggest change in how things are actually built?
Oh, without a doubt, the biggest practical shift is just the elevated standard of performance overall. I mean, the IECC pushed for enhanced R value requirements across all the key building parts.
Right.
But the real game changer, the thing that really shook things up, is the relentless focus on continuous insulation. CI, across wall assembly.
CI.
It's a move that's really intended to eliminate these inefficiencies that, frankly, traditional layered systems just couldn't solve.
I also see a huge focus on roofing standards in these sources, which, well, it makes sense, right? Heat rises.
Exactly. The code gives clear guidance there, focusing on energy-smart roofing with the insulation placed above the deck.
Yeah.
That's key. Above the deck to cut off those heat loss paths.
Above the deck, right?
And, crucially, the IECC standardizes definitions for all the heavy hitter materials. Mineral wool, rigid foam, spray foam. This makes sure everyone's speaking the same kind of high-performance language. Doesn't matter what climate they're building in.
Okay, let's really unpack this CI concept then. Continuous insulation.
Yeah.
Because for a contractor or maybe a developer, this is often the most complex part and sometimes, frankly, the most expensive requirement to meet. So what exactly is it, and why did the IECC basically make it mandatory for high-performance walls?
Okay, CI. It's simply an uninterrupted layer of thermal protection. It runs across the entire surface of the wall, including over the structural members like steel studs or wood framing. The key word is uninterrupted.
Got it.
It's often installed on the outside, placed between the wall sheathing and whatever the exterior cladding is, whether that's brick or metal panel or stucco.
And the reason CI is so powerful. You mentioned it fights thermal bridging. We've touched on that. But let's make sure everyone listening really understands what that phenomenon is.
Right, thermal bridging. It's essentially a fast lane for heat. Think of it like this. If you leave a metal spoon in a bowl of hot soup,
Yeah.
the handle gets hot really fast,
Right.
even though it's not in the soup. That metal is bridging the heat from the soup straight into the air.
Okay, I get that.
So in a commercial building, things like steel studs, they're excellent thermal conductors.
Mm-hmm.
If you only put insulation between those studs, the heat or the cold in winter just flows right through the steel framing itself. It bypasses your insulation completely. That structural bit, that's your thermal bridge.
Wow, that sounds like a potential disaster for efficiency. What kind of performance losses are we actually talking about if you just rely on that traditional, insulation between the studs method?
Significant losses. Really significant. Even in a wall that seems well insulated otherwise, thermal bridging through, say, steel studs can cut the effective R value of the whole wall assembly by maybe 30%,
Hmm.
sometimes even up to 50%.
50%.
Yeah. CI solves this because it completely wraps the structure. It prevents that conductive heat loss path, and it tightens up the building envelope dramatically. That's why CI is now, a code-mandated solution in many, many climate zones.
But okay, implementing CI, it must add layers of complexity, right? Especially when you're dealing with windows, doors, different cladding systems attaching. If the code says you have to do it, how do project managers balance that increased material and installation cost with the eventual energy savings? That seems like the real world trade-off.
That is the essential question, isn't it? It comes up in every construction meeting.
Right.
And yes, CI definitely requires careful detailing. Flashing around windows has to accommodate the extra depth of the exterior insulation. And the systems for attaching the cladding, they get more complex too. However, what the sources often show is that the payback period can be surprisingly short,
Mm.
especially when you factor in that you might be able to downsize the HVAC system. A
Oh.
quieter building just needs less heating and cooling capacity.
Hmm.
So that offsets some of that initial construction premium.
Mm.
CI delivers not just a building that meets code, but one that's fundamentally more durable and, frankly, just functions better.
Right.
And here's where it gets, well, I think really interesting. We move from these sort of universal requirements to more tailored knowledge,
Hmm.
the IECC's climate zone guidelines.
Okay.
You just cannot treat a building in, say, Seattle, which needs moderate heating, lots of moisture management, the same way you treat one down in Phoenix, which needs, extreme heat rejection.
So the building's location dictates the required R values, and that in turn pushes the use of specific materials. Let's look at the map concept for a second.
Exactly. So for instance, in the colder U.S. climate zones, think the Northeast, Upper Midwest, the IECC mandates significantly higher roof insulation R values. Sometimes you're looking at R38 or even higher for attic spaces.
Wow.
And that's specifically to hold on to interior heat and slash those winter energy bills.
Makes sense. Conversely then, in warmer zones, places with maybe milder winters but really brutal summers, is the strategy just about maximizing R value? Or do other things like, say, reflectivity come into play?
Oh, other factors are crucial in warm zones. The priority there is keeping heat out. So this is where materials like rigid foam board insulation, especially the type used for continuous exterior insulation, are really favored
Why is that?
because they're extremely effective at blocking radiant heat gain. They help keep interiors cooler and improve energy savings by acting as a complete thermal break on the outside.
Okay, that brings us squarely to picking the materials then. We can't just list them off. We need to talk about the real-world trade-offs, because that's critical for project decisions and ultimately performance. What are the pros and cons of those heavy hitters you mentioned in commercial insulation?
Good question. Let's start with spray foam insulation. Its huge advantage is its amazing air sealing capability. Plus, it has a very high R value per inch of thickness.
So it seals really well.
Exceptionally well. It's perfect for filling weirdly shaped gaps and creating a truly airtight envelope. But the downside, it comes at a higher install cost, and you need specialized crews and equipment to apply it correctly.
Okay. And what about the more maybe traditional options?
Right. Then you have mineral wool insulation. Now, what's fascinating here is that while its R value might be a bit lower than some foams, it's highly desirable in commercial buildings because it's inherently fire resistant.
Ah, fire resistance, key point.
Big point. And it also offers fantastic sound dampening qualities. So if you're building, say, a school or a hospital or even a densely packed office block, mineral wool addresses code requirements beyond just thermal performance. It hits fire safety and acoustics. That's a powerful trade-off to consider.
Yeah, that makes a lot of sense. And the material often used for that exterior CI layer you were talking about.
That's usually rigid foam board insulation. Typically, you see polyisocyanurate or polyiso and extruded polystyrene, XPS. It's ideal for continuous exterior use because it's relatively durable, it packs a high R value into a compact thickness, and it resists moisture quite well.
Okay. Any downsides?
Well, the sources often bring up environmental considerations, specifically around the blowing agents used in manufacturing some types of rigid foam. That can be a factor if you're aiming for, like, green building certification.
Right, LED points and things like that.
Exactly. And for enclosed spaces or maybe retrofits, we often see blown-in materials used.
Tell me about those.
Yeah. Blown-in insulation could be cellulose or fiberglass. It's perfect for retrofits, where you need to dense pack existing wall cavities, maybe without tearing down the entire structure.
Ah, less disruptive.
Much less. And cellulose in particular is often highlighted as an eco-friendly option since it's made from recycled materials. Plus, it performs exceptionally well in enclosed spaces, especially if it's properly air-sealed alongside it.
Okay, turning now to specific application areas. Because, while walls might get the glory for architectural design, roofs. Roofs are where a huge amount of heat loss can happen, just because of their sheer surface area, right?
Absolutely.
So what makes the current roof insulation standard so rigorous?
Roof insulation is definitely a top priority under the IECC, largely because it impacts the whole system's integrity. The standard practice now, as we mentioned, is placing that insulation above the deck.
Already above the structural part.
Correct, on top of the structural substrate, but underneath the waterproof membrane.
Hmm.
This method is just superior, really, for three key reasons.
Okay, tell us why.
First, pretty obviously, it delivers that continuous efficiency and minimizes thermal bridging through structural beams below. Second, and this is crucial, it actually protects the expensive roof membrane itself.
Protects the membrane. How?
By placing the insulation above the deck, you shield that membrane from the wild temperature, swings the thermal shock it would otherwise experience day in, day out. This can dramatically extend the life of the whole roof system.
That's huge. I never thought of that.
That is huge. And third, it helps manage condensation risk by keeping the deck temperature generally above the dew point.
Okay, that's a massive insight about protecting the membrane. So thinking about older buildings then, if I'm managing a project, say renovating an older commercial building, one that certainly wasn't built to today's IECC standards, how do I handle compliance? Are there practical ways through it for retrofits, or am I potentially facing, a full, prohibitively expensive demolition?
That's a common concern. Renovations do have to meet minimum insulation requirements, but the code is actually quite pragmatic about it. It provides practical pathways to get a performance upgrade without necessarily demanding a complete rebuild.
Okay, how so?
Well, you could often leverage the repair, alteration, and addition sections within the IECC. For example, if you're replacing the roof membrane anyway.
Yeah.
The code usually requires you to upgrade the insulation underneath it to the current minimum R value for that climate zone at the same time. It makes sense. You're already up there.
Right, bundle the work. But what if the existing wall cavities are just too narrow? Or they're filled with old, maybe degraded insulation? That seems like a major pain point.
That is the classic retrofit challenge. When those wall cavities are tight or problematic,
Yeah.
then exterior application options often become your most effective path to upgrading performance.
So adding insulation to the outside.
Exactly.
Yeah.
This might involve applying new CI, maybe rigid foam board externally, often then covered by an exterior insulation and finish system, or EIF, sometimes called synthetic stucco. This method lets you dramatically upgrade the thermal performance while keeping the interior structure pretty much undisturbed. Though, of course, it means dealing with new detailing around existing windows, doors, other penetrations.
Right. Complexities again.
Always complexities. But the code also allowed for adjustments. For instance, for buildings with historic designations, or maybe when the scope of work is very limited. Often this is done through performance modeling.
Performance modeling.
Yeah, using software to prove that the entire building, as a system, meets a mandated energy performance level, even if one specific component, maybe the walls, is slightly below the strict prescriptive R value requirement because of physical constraints.
Ah, okay, so there's some flexibility if you can prove overall performance. That makes sense.
Exactly.
So let's bring it all together. What does this all mean for you, the listener? Whether you're the one signing off on permits or designing the building or maybe managing the construction budget, what is the bottom line value, really, of embracing these high-performance mandates?
Well, compliance is, yes, it's a legal threshold. You have to meet it. And doing so ensures you get smooth approval of permits, timely project progress. Yeah. Basically, it prevents expensive delays.
Which nobody wants.
Nobody wants delays. But the advantages go much, much deeper than just avoiding trouble. Proper insulation results in vastly lower energy costs over the building's life. And it provides stronger, more reliable building performance for decades. It's really a foundational quality metric.
And if we look really long term, this system, this proper insulation, it directly supports enhanced property value, doesn't it? And
Yeah.
maybe even lead to more favorable insurance terms because you've minimized risks like moisture and mold that come with bad thermal envelopes.
Absolutely. It's truly an investment in asset protection,
Yeah.
not just an expense. So that's really the takeaway mandate here. Always consult the current commercial construction regulations and the code-specified insulation benchmarks before you even think about laying a single foundation or starting a major reno. Understanding the why behind the IECC, the push for CI, the focus on R value, the tailored climate approach, it safeguards your investment and ultimately elevates the function of the entire building.
That brings us towards the end of our deep dive for today. Just to quickly recap the essential nuggets we've extracted for you, the IECC outlines critical thermal performance standards for all commercial buildings, demanding verifiable R values tailored to the specific climate zone.
Right.
Continuous insulation, or CI, is really prioritized because it prevents thermal bridging. Remember that fast lane for heat loss through studs and beams, and it's often mandatory now.
Very often.
And for roofs, putting insulation above the deck is now standard practice because it maximizes efficiency and protects that expensive roof membrane from thermal shock and degradation.
Key points, all of them. And here is a final thought for you to consider, kind of building on that principle of location-specific performance we talked about.
Okay.
If tailoring insulation, the R values, the material choices to local climate zones, is so critical for maximizing building performance and saving money, what other overlooked or maybe traditionally standardized system in commercial buildings might benefit most from similar location-based regulation? Think about perhaps HVAC zoning strategies or maybe envelope glazing specifications.
Yeah.
Could they be better tailored to perform optimally given very specific local environmental stressors like prevailing wind or high humidity or intense sunlight exposure?
That's interesting, applying that climate zone logic elsewhere.
Exactly. Just something to consider next time you're looking at a set of blueprints.